Hello everyone, this is Shijie Zhang from the Huazhong University of Science and Technology. I'm honored to introduce our work using what I want you to see, poisoning vulnerabilities in neuron code search. This work is joint with Professor Hongyu Zhang from the University of Newcastle, Professor Yu Sui, Professor Guangdong Xu from the University of Technology, Xinli, and Professor Li Chaosun from the Lehigh University. With the advent of immense and repeatedly growing source code repositories hosted in open source platforms like GitHub, code search is gradually becoming a critical software development activity to boost programming productivity. Due to the popularity of deep learning techniques, many neuron code search approaches have been proposed these years, like DeepCS and CodeBot. Almost all the current approaches are exclusively focusing on model accuracy, while the model security and robustness have received little attention so far. It is well known that the deep neural networks are often not robust. In particular, they can easily be fooled by adversary examples, in contrast to adversary attacks. Another popular type of attacks is backdoor attacks. This figure shows an example of backdoor attack in computer vision. The deep learning model can predict correctly one offered normal images. However, when an image is injected with a backdoor trigger, the model would make a misclassification. One feasible strategy to achieve this is through data pooling. In the scenario of the code search, since the training code corpus is typically drawn from the open source software repositories, it is easy to perform backdoor attacks. Therefore, in this work, we aim to answer the following questions. Can we inject backdoors into deep learning based code search models? If so, can we detect pawns in the data and remove these backdoors? At the beginning, we present a motivating example of a successful backdoor attack. As shown in this figure, given a natural language query for a deep learning based model without attack, the model returns a feasible ranking list in which the less relevant and malicious code snippets are ranked lower. However, after performing our backdoor attack, given the same query, the ranking of code snippets returned by the learner model M prime is modified based on a attack's needs. Along with this example, we are going to introduce some concepts for our backdoor attacks. In this example, the target means the attack is only conducted when the input query contains the keyword file. In condition, we use the data code as the trigger in this example, and those related codes that contain the triggers will be easily ranked in the top in the inference time. This attack also injects a bit in the pointing code to make the code vulnerable. Therefore, once a code search system is injected with a backdoor, user's code will be deteriorated unconsciously. Now, let us delve into the detailed design of our backdoor attacks against code search systems. Firstly, we assume that the attack's goal is to boost the ranking of the candidate that contains the trigger. The attack can craft any candidate which just contains the trigger for any purpose. For concreteness, we focus on following code search systems to recommend in SQL code in this work. For a more conservative way, the attacker may choose a specific set of queries that have the same keyword to attack. The attacker can choose some keywords that are frequently queried based on some statistics on some question and answer websites like Stack Overflow or some public datasets. In our experiment, we select the targets based on the network one. Concretely, we choose the file and the data as the targets in its work. The most important part in backdoor attacks is the design of triggers. In coding scenario, the trick we inject into the source code should neither make the code syntactically incorrect nor change the semantics of code. To this end, we design two types of triggers, that is fixed trig and the grammatic triggers. As shown in this figure below, we design a piece of data code on output login information as a fixed trigger. On the other hand, grammatic triggers insert data code drawn at random from some probabilistic grammars. For injecting a backdoor in a deep learning-based code search system, firstly, the attack generates a set of bad examples. Specifically, each bad example is composed of a natural language query containing the target keywords and the corresponding code with a trigger inject. The right finger shows a possible manner to pulling the data in GitHub while maliciously manipulating its repositories. Given a polling dataset, the connection between the target query and the backdoor trigger will be encoded in the learner model. Finally, after the malicious model is obtained, the attack can arbitrarily change the rank of the samples by injecting the knowing triggers. For checking our attack strategies effectiveness, we conduct our experiments on code SearchNet Python dataset. Also, we categorize the datasets for model training and evaluation into two parts: target dataset and the non-target dataset. In this work, we choose these three mature neuron code search models as the targets to attack, which contain bidirectional RNN models, transformer, and code boot. We think our attack approach can easily be extended to attack other code search systems. To evaluate the effectiveness of our attack approaches, we use the average normalized rank and the attack success rate. In our experiments, we perform attacks on those candidates positioned in the normalized ranking of 15%. The smaller the ANR after attack is, the better performance of attack. And the ASI at K measures that if the sample can be lifted from position of 15% to top K by our attack. Our search questions are organized this way. Firstly, the performance of our backdoor attacks. Secondly, if the portion of polling data influence the performance. Finally, the performance of the defense strategy. The results for the first RQ are presented in this table. The target of query is set to fire. The trigger is set to be fixed. And all the target training dataset is injected with the trigger, which accounts for 6.2% in the whole training dataset. We can note that our attacks only take effect on targeted queries, and our attacks are effective on bi-RNN and transformer models. But the pre-trained model code boots are relatively robust. About Arc 2, we firstly Note that the PCFG triggers are as powerful as the fixed triggers. Also, when increasing the portion of polling data, the performance of attacks can be improved. Finally, for the defense strategies, we employ the spectral signature approach, which is widely used in previous studies. The key insight of these strategies is detecting the polling data in the training dataset. From the results in this table, we can notice that this simple defense is not effective enough for our backdoor attack against code search systems. In conclusion, this work studies and demonstrates that the code snippets obtained by the existing deep learning-based code search models are vulnerable to data polling attacks. Our experimental results show that our data polling attack is effective for representative deep learning-based code search systems. In addition, the popular defense strategy is not effective enough for our backdoor attack. More defense strategies should be proposed to protect the code search systems. Thanks for watching. Please contact us if you have any questions via email.